Hey guys, this is Coach Brian bringing you your 9.4 notes about even, odd, and co-functions. So to begin with, we're going to simply define even and odd functions. And in previous classes, you've talked about even and odd functions. You may have heard that even functions, if they're even, you could fold them along the y-axis because they would be symmetrical about the y-axis. If they were odd, you could rotate them around the origin. You might have even, heard some things like that they're symmetrical about the y or symmetrical about the origin. You may have even talked about their end behavior. If graphs are even, typically the end behavior goes in the same direction. So both ends will go up, both ends might go down. If it's odd, they're usually going to alternate. If one end's going down, the other's going up, and vice versa. Today we're going to talk about algebraically even and odd functions. So if we look at this first statement, there's kind of two things to look at here. One, we want to look at our x's here. Okay, one has a negative sign in front of it. They're both x's, but one's positive and one's negative. So we would say they have opposite inputs. But what you'll see is when I put in the negative number, I get the output of the regular x. So that can be a little confusing if you're not comfortable with this notation, but pretty much what I get is if I put in the opposite input, I get matching outputs. And that's an even function. So let's say like I have a function. I'm not going to create a whole one here, but let's say I have a function and I plug in a 4 and I get out 16. And in that same function, I plug in a negative 4 and I get out a 16. That would be considered an even function. For our next one, you'll see here that the input is negative, or what we would call opposite. We'd say opposite input. But now I'm not getting the exact same output. I'm getting the same value, but it's negative. So it'd say opposite output. So for this, again, just to rewrite it over, we have opposite inputs, and we get an opposite output. And this is an odd function. So again, as an example, let's say I put in f of 2, and I get out 20, but I put in a negative 2, the opposite input, I'm going to get out a negative 20. So that's how odd functions work. If we're looking at these two graphically, all right, this first one here says examples of even functions. So we've got some even functions here. Don't know why that made an arrow instead of a box. We've got some even functions. This first one is x squared, and this one is 1 over x squared. And graphically, if I plug in, let's look at this. If I plug in a 3 here, my result or my output would be 3 squared, which is 9. So I go over to 3, go up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, so I'd be right here at 3, 9. But let's look what I get in if I put in a negative 3. I'd get negative 3 squared. Well, negative 3 times negative 3 is also 9. So you can see I put in opposite inputs, but I got the same output. I got the same result. Now if we're looking at 1 over x squared, if I put in a 3, that'd be 1 over 3 squared, which is 1 over 9. Be right over here. And if I put in a negative 3, it'd be 1 over negative 3 squared, which is also 1 over 9, which is right over here. So same thing, I put in a plus 3, I put in a negative 3, and if you look at my outputs, I got the same result, same output. So this is how even functions work. You can put in values with opposite signs, but you're going to get matching results or outputs. Looking at odd functions, you'll see that when I put in the positive version of a number and the negative version of a number, I'm going to get different results. 3 cubed, 3 times 3 times 3 is 27. However, negative 3 times negative 3 times negative 3 gives me negative 27. So put in a 3, get out, I know 3 is right here, so 27 will be way up here somewhere. Put in a negative 3, get out negative 27. So much different than our even functions, because when I put in the negative version of the number, I get a negative result. Another good way to think about it is that for an odd function, if the negative's in here and you end up with a negative answer there, the negative went from in to out. The negative sign did. Let's look at this one. It's just 1 over x. So this one would be, if I plug in a 3, I get 1 over 3. If I plug in a negative 3, I get 1 over negative 3. Again, these are opposite outputs for an odd function. Now let's look at the trig functions, all right? So far, when you've learned this, one thing you've probably focused a lot on is the powers. See how this is a 3 and a root 3, and this is technically a 1. So all of these have odd exponents, and if you look up at the even, see how it's a 2 and a 2, and a lot of the focus has been put on exponents, but that doesn't always apply to the different functions. So what we need to do is we need to really focus in on this algebraic definition of them, these two right here. We really need to focus on these as we are discussing odd and even functions. So we're going to keep this in mind, these rules about inputs and outputs, and we're going to look at the trig functions. So determine if each value is positive or negative. And you can see my input now is an angle. So essentially it's saying if I put in a positive angle and I put in the negative measure of that same angle, how do my results vary, if they do at all? So if I were to look at this angle, theta, and find the sine of it, I would need to go opposite, which is my y, and hypotenuse, which is my r. So it would be r over y, and in this case, they are both positive. Don't forget, r is always positive. But they're both positive, so r over y would give me a positive over a positive. However, let's look at negative theta. It's the same angle, but instead of going in a positive way, we've now opened up clockwise or in a negative way. And to find the sine of this angle, I would go across or opposite, which is my y, and then I would go to my hypotenuse, which is my r. Well, again, we said r is always positive, but in this case, y is down, and when y moves down, it's a negative number. So in this case, I totally said this backwards. Sorry, I just realized this. Sine is y over r. I'm sorry. That distracted me. Now I'm on sine negative y, which again is y over r, but if I use these from quadrant 4, y is negative and r always is positive. But I want you to see that these two answers vary because this would end up being positive and this would end up being negative. So I plug in a positive, or the positive version of a number, and I got out a positive answer. Here I plug in the negative of that same input and I got out the opposite or negative. So because of that, that makes sine, the fact that these two results were opposite, that makes sine an odd function. Now, using our same angles, and I'm going to move a little bit quicker now, we would look at cosine. And for cosine of this angle, we would use the adjacent, or the x, and the r. X over r. Cosine is x over r. And in this case, x, since it's going to the right, x is positive and r is positive. So for the positive theta, it'd be positive over positive, which would ultimately result in a positive. And for cosine negative theta, I would use adjacent and r, or hypotenuse. So I would use x, which is going to the right, and r, which is always positive. And so for cosine, I would also get, cosine of negative theta, I would also get a positive over a positive, which would result in a positive. And now we can see that these match. Even though we put in opposite inputs, we put in a positive theta here, but we put in a negative theta here. We put in the same value but different signs, and we got matching answers, which means cosine is an even function. Cosine is an even function. And now lastly, we'll look at tangent. If I'm looking specifically at tangent, I'm using the opposite and the adjacent. In this case, it'd be y over x. Excuse me. It'd be y over x for both. Excuse me. I'm not re-recording this though. I'm sorry. All right. So going over here and looking at my opposite, that's positive. Looking at my x, that's positive. So for tangent of positive theta, it's a positive over a positive, which would result in a positive answer. When I go look at my negative theta, I'm looking still at opposite over adjacent. This y is negative. This x is positive. So when I do y over x, I get negative over positive, which is negative. So again, you can see I put in opposite inputs. However, I also got opposite answers. And since I put in opposite input and I got an opposite answer or solution, that means tangent is an odd function. Tangent is an odd function. So if I go look at these three, I just want this to look like the rest, sorry. If I go look at these three, cosine is my only even function, okay? It's my only even function. However, these even and odd rules also apply to the reciprocals. So not only is cosine odd, so is cosecant. And not only is cosine even, but so is secant. And not only is tangent odd, but so is, sorry, that's a horrible arrow. so is cotangent. So the trig identities and their reciprocals share these even-odd properties. And here's just a little reminder, reference for you. So one thing I want to point out again is that if you plug in a negative and your answer is negative or opposite, that's going to be your odd. All right, that's going to be your odd. But if you plug in the opposite and you still get out the same or the positive solution, that's going to be your even. So think about it. If I plug in opposite things, do I get opposite answers or do I get matching answers? That's kind of the question to ask yourself for even and odd. All right, so now we're going to rewrite each expression with a positive argument using the odd-even properties. All right, so to begin with here, we need to define argument. What is argument? Argument is the number or value inside the parentheses. So if you want to make a little note of that, you can. It's the value inside the parentheses or inside the function. So in this case, sine is an odd function. And 70 right now is negative. So if I wanted the argument to be positive, I could rewrite this, since it's an odd function, as negative sine 70. See how if I go up here, if I have a negative input, I can bring the negative out front. Secant, because it's the reciprocal of cosine, is an even function. What that means is if I have a negative argument, I can just rewrite it as the secant of 25. Because it's even, these opposite inputs will give me the same result. Tangent is an odd function. Because of that, since the negative right here is inside the parentheses, I can move it out front. Next, we're going to talk about some cofunctions. Cofunctions, the co in cofunction stands for complementary. And that's complementary with an E because it means like to complete something. Not to say something nice about it, but to complete something. So thinking back to geometry, if we said, what's the complement of 36? Well, complementary things add up to 90 degrees. So to find the complement, you would take 90 minus 36, and that would leave you with 54. So 54 degrees is the complement of 36. So trig functions, trig identities have this quality to where the cosine of an angle, or the sine of an angle, this also works in reverse, but the cosine of an angle equals the sine of the angle's complement. So for instance, if you had the sine of 36, that would be the same thing as the cosine of 54 because these two angles together equal 90. They're complementary. So just for some practice, for the sine of 20, I could go with the opposite, so cosine, and then I could get the complement. So whatever 90 minus 20 is, 70. Those two things are equal. For cosine, I would go to sine And the complement of 36 is 54. It's going to be the number that adds up to 90 with it. So these two functions are called cofunctions, and we can map these out on our hexagon. And we don't have to do anything differently than we've been doing. We'd start with cotangent, or I don't know why I would do that. We'd start with tangent on the left and cotangent across from it. And then if you can remember that tangent equals sine over cosine, you'll have it nailed because you can go across and you can do the reciprocal functions. You can go across and do the reciprocal functions. And so we've got everything in place. The complementary functions, this is just another use of our hexagon here. The complementary functions are across the hexagon. I would say in line with each other. Let's put it like that. They are in line with each other. So sine and cosine are complementary. Tangent and cotangent are complementary. Secant and cosecant are complementary. Again, if you're unsure about this, you could always check it on your calculator. You could plug in degree mode, you could plug in sine 20 and you could plug in cosine 70 and they should match. You could plug in cosine 36 and sine 54 and they should match. So using our hexagon, I'm going to say, what is the cofunction of the tangent? What's the cofunction of the tangent? So I just need to find which one is in line with it on my hexagon, and that would give me the cotangent. Cofunction of the secant, I would just go down here and say which one's in line with it. That would be the cosecant. And then we've got some cofunction identities. We would say that sine of theta equals the cosine of 90 minus whatever theta is. This is just what we just did. Like if we said the sine of 20, it would be, the cofunction would be the cosine of 90 minus 20, which would just be 70. And if you were working in radians, you would want to subtract everything from 2 pi, because remember 2 pi is 90 degrees. 2 pi is 90 degrees. So let's put these to use, all right? Let's put them to use. We've got the cosecant of 35, cosecant of 35. So if you need to refer to your sheet up here, you can. But since this is in degrees and cosecant is a cofunction of secant, I'm going to use 90 minus 35 to find my complement. And that gives me that the cosecant of 35 is equal to the secant of 55. Make that look a little more like a 5. It's the secant of 55 degrees, and those two things are equal. Tangent's cofunction is cotangent, and so I'm going to do 90 minus 15. And so the tangent of 15 is equivalent to the cotangent of 75. Now where it gets a little tougher is with radians. I have the tangent of 2 pi over 7. And that's going to equal the cotangent of pi over 2 minus 2 pi over 7. And where this gets a little tricky is that I cannot subtract these fractions without a common denominator. I have to have a common denominator. So we kind of worked on this in class for 9-2, and it's a good skill to have in general. You could just say that the cotangent is going to be pi over 2, And see how this denominator is a 7? I'm going to multiply this by 7 over 7. And then I'm going to subtract. And over here, I've got 2 pi over 7. And you see how this one has a 2? I'm just going to multiply that by 2 over 2. When I simplify these things through multiplication, it gives me 7 pi over 14. And I'm taking away 4 pi over 14. So 7 minus 4 leaves me 3 pi, and that's over 14. So this whole thing right here also equals the cotangent of 3 pi over 14. On the right side, I've got sine, so I know I'm going to be going to cosine, and I want to take 90, or pi over 2, and subtract pi over 9. Again, these do not have common denominators, so for my first one, I'm going to do pi over 2. I'm going to take the 9 from this denominator and multiply it by 9 over 9. And I'm subtracting, so I'm going to subtract pi over 9, and I'm going to use the 2 from this guy, the 2 right there, and multiply this by 2 over 2. So as I work that out, my final answer should be the cosine of 9 pi over 18 minus 2 pi over 18, which reduces to 7 pi over 18. Again, that's the cosine of 7 pi over 18. All right, there's some you try it problems that you should try before moving on to your classwork and exit ticket. Hopefully this helped you understand even and odd functions and co-functions. Before I go, I just want to make one last little quick note, one last, maybe not easy way to remember, but a little note to help you. And that note is when you have even functions, you're going to plug in opposite inputs, but you're going to get identical outputs. Remember, input is what you put in the function. Output is what you get out of the function. And when they are odd, you're going to put in opposite inputs, but you're also going to get out opposite outputs. And one last time, an example of even would be if I put in a 2 to a function and I got out 10, but I put in a negative 2 and I also get out a 10. And an example of an odd function would be if I have a function and I put in 5 and I get out 27, but I put in a negative 5 and my answer is negative 27. And it doesn't always, I know I'm rambling a little bit, it doesn't always have to match. Like the signs don't have to match. So let's say I put in, let me just flip this one on its head a little bit. Let's say I put in a 5, but I got out negative 16. And then I put in a negative 5 and I get out positive 16. That's okay. The thing you need to look at is that these are opposite, my two inputs, and these are opposite, my two outputs. Okay? If the answers and the inputs are opposite, that's odd. If the inputs are opposite, but the outputs match, that's even. Hopefully that helps. Have a good day.